Hello again, my dear students, and welcome to the final part with our chapter number 2 or lecture number 2, electrical p-n junction dots. If you remember, my dear students, in the previous parts, we have dealt with the standard or the typical IV characteristic curve for an electrical light, including the forward bias, reverse bias, and the breakdown. And we start to model this electrical diode as a circuit element. We started with what we call the ideal model, which is the most simple one. Whenever you transfer your electrical diode into a short circuit, as far as it's a forward, and it's an open circuit as far as it's reverse. And then we have integrated our electrical diode as an ideal device in a series of AC and DC examples. Then we go to the typical solution or the graphical based solution when we use the experimental model and the load line. And we have mentioned that the intersection point between the IV characteristic curve, the exponential forward bias IV characteristic curve, and the load line indicates the operating point. However, we have mentioned that this technique is somehow difficult to be implemented analytically, and it needs some sort of a graphical solution or a numerical solution in order to get an accurate intersection point between these two functions, a linear function and an exponential function. Accordingly, we start to introduce some in-between model. What I mean by in-between, that it's not that easy like the ideal model, and it's not that sophisticated like in the case of the graphical or the experimental model. Herein we introduce two models. The first, what we call the piecewise linear model, where we replace the diode by an ideal light, just to indicate open circuit or short circuit, a built-in potential, reverse bias voltage, and a forward resistance, or what we call an RD. And this what we call the piecewise linear model. Next, we also introduce another less complicated model, which we call the constant voltage model, where we assume that this forward resistance is somehow tends to zero, it becomes a short circuit, and then you have only an ideal line along with the built-in potential. So we start to examine the utility, the effectiveness, or the accuracy of these three models. We consider this circuit and we start to solve this circuit 3 times, each using a different model, starting from the most simple one, which is ideal. Then we have the constant voltage model, and finally we have the piecewise linear model. And by using this and comparing our output with the exact output, you can examine the effectiveness or the accuracy of the model. Of course, it can be easily concluded that the piecewise linear model is the most accurate model with respect to the exact or the graphical solution model. And then the ideal model is the lowest accuracy. So it's simplicity against accuracy. Whenever you are seeking for simplicity, you are going to use an ideal diode. However, please expect that your accuracy will not be that good. And the vice versa whenever you go to the piecewise linear model. Okay, that's perfect. Now, what we are going to do in this final part, my dear students, is that we are going to investigate some potential application where diode play an important role in, as well as we are going to demonstrate what we call the Zener diode. So let's start with the application. Maybe you already have seen this diagram before. I believe that in your circuits module, you have already used this bar diagram in order to implement your project dealing with the DC power supplies. And in this, you have examined the first block, which is directly after the transformer, which is the rectifier. Transformers are those devices that step up or step down the voltage based on your needs. So in this case, you have the AC line which is 220 voltage RMS, and you need to step it down for 12, 15, whatever it is, then you are going to use transformers. Maybe you will know more about transformers in your next year courses whenever you are dealing with electrical power systems. Now, after the transformer, you still have an AC signal. However, its amplitude is less. reduced, but it's still an AC. And in order to transfer it finally to a DC, you have to use what's called a rectifier. So what we are going to tackle now is how we can use this diode in implementing either a half-wave rectifier or a full-wave rectifier. Now let's start. Okay, so what is the half-wave or what is the full-wave rectifier? Let's start with the half-wave rectifier. Here, as you can see, we have a transformer. You can actually neglect this transformer. By the end of the day, this plus minus Vs is a normal AC voltage with an amplitude called Vs. Now let's use the most accurate model, which is a piecewise linear model. In the piecewise linear model, we have first to distinguish if our diode is a forward or is a reverse. Whenever it's a reverse, then it's an open circuit, so there is nothing connected. However, whenever it's forward, you are going to replace this with an ideal diode, a battery, and a resistance. So let's now start to do this experiment together and to see how this will affect our output. Okay, perfect. So this is our circuit. We have plus minus Vs coming from the transformer, applied on a diode, and then you have your load. This is RL, which indicates L. Now, what is Vs? Vs is a sinusoidal input, as you know. And so on. Okay. For this sinusoidal input, you know, as it's an AC alternating current circuit, then it has two, let's say, polarities. In the positive half cycle in this region, that's highlighted with a different color. In this positive half cycle, you have a positive voltage. So whenever you have a positive voltage, then the voltage on the anode is greater than the voltage in the cathode, and your diode is on. So in this case, we have a forward bias diode. However, in the reverse case, whenever the voltage is negative, then you will have a diode which is in the reverse bias, because simply this anode voltage will be negative. That means that it's against the direction of the diode, and your diode will be reversed. So what should we do in case it's forward or in case it's reverse? So if your circuit is in a forward bias, I mean in the positive half cycle of your output, then you will get something like that. So you have this positive negative Vs, you have now this, and now you have a battery and a resistance, which we call it RD, and this is the load, which is RL. What if it's reverse? Then you have an open circuit and a resistance. So this is the two conditions. This is a forward bias condition, and this is a reverse bias condition. Let's start with the easiest, which is the reverse bias. Whenever it's a reverse bias, then this is simply mean that it's an open circuit. No current will reach the load. This V output will E equals to 0. So in the reverse bias, you will get 0. No output. Okay, so what about the forward bias? In the forward bias, we have this battery, which we call it VBI or V built in, or sometimes we call it V node. Both are the same meaning. And we have RD and RS. Let's start to solve this circuit somehow. So we have here Vs, then we have this battery, then we have a resistance called RD, and then we have the resistance, which is R load or the load resistance. Okay, so what about the voltage here? What about the voltage at these 2 points? It's very easy. As you can see, it's Vs minus V building. That's true. So the voltage here, or very basically, if you compare this node with this node, if this node have a voltage Vs, then this node will have a voltage Vs minus the building potential, VBR or VE. Now, then we have a potential divider between R load and RD. So the output here is simply Vs minus V node times R load over R load plus RD. This is the answer. The most optimistic model when this R load is very, very, very small. Let's say that this R load tends to 0, it's a short circuit. Then this term will tend to 1, and your V output will be S minus V load. Accordingly, whenever you start to plot the positive half cycle, which is this one, this is the input, of course. Whenever you start to plot this output here, if this input has a maximum value called Vs, you should expect the output to be something like that. Vs minus V node. And this is, again, the most optimistic output. Because if you have an RD, then the output will be Vs minus V node times RL over RL plus RD. What I just need to highlight here that we have first implement what's called a half-wave rectifier circuit. The target of this half-wave rectifier circuit is to get rid from the negative half cycle, and then we have only the positive half cycle. The second is please expect losses in the positive half cycle. So whenever you have an input Vs, your output will be at least Vs minus V. So you have a reduced your output. So if we plot these together, this difference represents V node or the voltage drop. This is the input, and this is the output. So please take care about it. So this is the voltage drop due to that diode, due to having the diode in order to make this half-wave rectifier. Perfect. So this is what's called the half-wave rectifier. Can we implement a full wave rectifier? Yes, we can. We have actually 2 models for the full wave rectifier. Let's start discussing this one. The first model is what we call the bipolar transformers. What is a bipolar transformer? So let me start plotting. So we have a transformer here. The normal transformer has 2 inputs, 2 outputs, as the one we mentioned in the first example. But now this transformer has 2 inputs and 3 outputs. So we have something like here. We have this diode, which we call it D1. Then this is connected to a load, which is RL. And we have also another diode here, but in a reverse direction. Sorry, in a reverse polarity. And it's connected like this. And we have a ground terminal here. Which is connected like this. The voltage here is plus minus Vs, and the voltage here is plus minus Vs. But please take care that now this terminal is connected to the positive, and this terminal is connected to the negative. Okay. So, how this circuit will start to work? Let's see. Let's first start to express with our input. We have an input like this. This is our input. Again, we can distinguish this input into 2 levels or into 2 stages. The first, we have the positive half cycle, and this is the negative half cycle. Okay. In the positive half cycle, your voltage is positive. Let's say, for example, we are in this point. Let's say that this is 12 volts. Let's say, for example. Okay. If we are going to reflect this point on the circuit, then we are going to say that I have plus minus 12 here and plus minus 12 here. And this is a common ground. That means that you are connecting your D1 anode into a plus 12 voltage. Accordingly, of course, this diode will be a forward bias. However, your reverse diode will be, oh sorry, not your reverse, your D2 diode, this is, we call it D2. So your D2 diode will be connected to the anode of D2 will be connected to a negative 12. So it will be a reverse bias. Accordingly, you can skip this diode. This will be an open circuit, so this wire is no longer existing. And what you can see now that you have a positive 12 connected to the load and a ground. So the output will be typically the input, but please don't forget that due to this die, you will have an output, a V node drop. So the output in this case will be the same Vs, but substituted with V node, which is the built-in potential for the diode D1. Typically, like what we did in the first example, if you remember, when we have an output less than the input by V node. So this is typically the same. You have this diode on, so it's connected like this. Okay, so this is the first stage. What about the second stage? When we start working in this point, for example, which is, for example, negative 12. Now, the voltage here is negative 12. So this point will be negative 12. And this point indicates the reverse polarity. Then this will be positive 12. So we have negative 12 here and positive 12 here. Negative 12 here, this means that this diode is open circuit. It's a reverse bias diode. And positive 12 here means that this diode is forward. Now you pass positive 12 to the load. This is an open circuit, no longer exists, and this is again connected as ground. So you are now supplying again a positive 12, but this positive 12 is coming from this down link, not from this one, because this one now is open circuit, and this is the short circuit one. So now you have again a positive voltage, but please don't forget that you have a voltage drop here V node, so you will get an output like that. Again with the same amplitude, which is Vs minus V node. So this is typically what we call a full wave rectifier. In a full wave rectifier, we not only pass the input when it's a positive half cycle, but we also alternate the negative to be positive. We fully rectify the signal. However, in the half wave rectifier, we only pass the forward stage, and we pass 0 whenever it's a negative half cycle. This is the difference between having a half wave rectifier and a full wave rectifier. Okay, back to my presentation. So this is a half wave rectifier, and this is the full wave rectifier, as you can see, my dear students, and this is the output of the signal, which is a full wave rectified. Again, please expect a losses, which is at least V node. It may increase whenever you have a higher RD or a forward resistance for the diode. Okay, another implementation for the full wave rectifier, which is one of the most famous application for an electrical diode. I believe, I'm quite sure that you have already seen this graph before, or this schematic before, during your circuit project, which is the bridge, the full rectifier bridge. It's a very easy way to implement a full wave rectifier. Let's see together. Here we have a direct transformer, positive negative Vs, and we have these 4 diodes connected in this manner, in this bridge manner. Whenever you have a positive, sorry, whenever you have a positive voltage applied in this terminal, then as far as this point is positive and this is somehow ground, then this D4 will be open circuit and D1 will be a short circuit or will be forward. So no current will pass in this branch, and all the current will pass here, will pass in this branch. And then at this stage, you will find two options. Either to go in this direction, which is again makes this diode reverse, so D3 is reversed, or to go in the resistance and then to go to D2. So the first pass in the positive half cycle to have this D1, the resistance R, and D2, and back to the negative terminal. This is the first pass. However, when you are in the negative half cycle, so this VS terminal to be negative, then that means that you will start your journey from here. This will be the positive terminal. So you will start with D3, and you will go through the resistance, and then with D4, where D1 and D2 will be off. So you have the same output, which is a full wave rectified signal. However, in your journey from the positive terminal to the negative terminal, you will pass by two diodes, not only one. That's why the voltage drop here between the output and the input is greater, is larger. It's V node or two building potential, not one. In this scenario, you have only one diode in your path between the source and the load. However, herein you have two diodes in your path between the source and the load. That's why that voltage drop here is greater. This is what's called the bridge. It's very famous, and it's usually used in many applications related to the motor operations and all this stuff. So this is one of the interesting applications where diode can play an important role in. Now let's turn to another circuit, which what we call the rectifier with a filter capacitor, a capacitor and a rectifier. And this is again usually used in the AC to DC power supplies. As you can see, if you return back to this slide, this filter stage. So you can have an high current plug that makes a full rectifier as well as a filter. Let's see the circuit. Okay, here let's see what will happen between the input and output. Whenever you have a positive half cycle, then this diode is a forward bias. And whenever this diode is a forward bias, that means that the current is flowing here and going inside the capacitor to charge the capacitor. So capacitors are going to be charged till you reach a maximum, and you start to decrease. Whenever you reach this maximum, that means that this capacitor is fully charged. And herein, the capacitor will start to discharge until you reach the same voltage again. Then you are going to charge again, and then discharge, and so on. Herein, we have a double function. First, we have rectified our AC signal because we simply don't have in the output, we don't have any negative voltage. As you can see, all the blue curve is in the positive voltage. Second, you have rectified, you have filtered this AC so that you get this something like that, which is the output for a filter, as you can see. So you have just a voltage regulator in order to regulate it into a pure DC. So this is one of the most simple ways in order to implement a DC power supply. Of course, generally speaking, if you go to literature, you will find more and more sophisticated filters than that. This is the most simple filter. You can make a better filters. Whenever you go this, you scale up this circuit to a better RLRC and RLC filters. And this is, of course, accessible in many documents over the internet. Now, this is our bonus question for this lecture. This is what we call the voltage doubler. Herein, we propose that the output voltage here on the RL will be double the input voltage. My question is, can you please prove this? Can you please prove that the output voltage here is double the input voltage? So you step up the voltage, or what we can call you boost the voltage. This is one of the famous applications in what we call the DC-DC converters, in order to convert or to step up a DC or an AC signal into a higher value. So you can examine this here, and you can see that this double voltage doubler circuit, which is one of the tricky circuits using the dot. Okay, now let's terminate this lecture with a very interesting part, which is the Zener dots. What is the Zener dots? A Zener diode is some sort of electrical dots, which has a very interesting IV characteristic curve, but in the reverse direction, not in the forward. In the forward, it's just a normal dot with a variable gain 0.7 or 0.5 or whatever. However, it's very interesting in the output, because in the reverse bias, it can clip the voltage to what's called the VZ. What do you mean by clip? I mean, whenever you increase your input, your output will be limited to VZ. For example, if you have an input which is 5 volts, and you pass it in a Zener dot, which has a VZ of 3 voltage in the reverse bias, then what will pass will be only the 3, not the 5. So you clip or you limit your voltage in the reverse to what's called VZ. We have already tackled the Zener effect as a breakdown effect in the solid state courses before. However, we are not now interested to remember those. We are just dealing with as a circuit element. So you can access the solid state electronic courses in order to remember what is the Zener breakdown and how it's technically or conceptually how it occurs. But now we are no longer interested in those, and we are going to make it as a circuit. So let's see how we are going to use this. This is an example. Let's go together and solve this example and see how we are going to use this Zener dot in a very interesting application. Okay, so in this example, we have, let me somehow fix the camera. Okay, perfect. Okay, so in this example, we have an AC source, a resistance, okay, let's call it R, and a Zener dot, which is in this direction. Usually in the circuits, we use this waved structure in order to distinguish between the normal diodes and Zener diodes. In the normal diodes, you have a straight line. In the Zeners, you have this wave structure. So this is just a circuit element or a circuit symbol to distinguish them. Now, we have two options. We have the positive half cycle and the negative half cycle. Okay. What will happen? Let's see. In the positive half cycle, this voltage is positive. That means that this voltage is positive. So current should flow in this direction, which is against the diode direction. Accordingly, you have a reverse bias. Now the question is, what is the behavior of this diode, of this reverse bias diode, of this Zener diode in the reverse bias? Let's make it numerical in order to make it easier. Let's say that this voltage is 5 volts. And that we have a Zener diode with VZ equals to 3, for example. Then, what the Zener diode will make is as follows. It will pass the voltage up to the 3 voltage. So whenever the input is less than 3, the output is typically the input. And then it would clip the voltage to 3 voltage. So once the voltage is greater than 5, the output will be equals to 3. And then it's drop back in this area. Okay. This and the behavior is the reverse bias. What about the forward bias? It's a very normal diode. So whenever you have a negative positive, I mean in the negative half cycle, now the voltage here is positive and the voltage here is negative. The current is flowing here in this direction from down to up, and then this diode is in a forward bias. Then you are going to replace this diode with a battery as usual. So the voltage drop here will be negative ripple in as usual. This is a very normal behavior. So in the reverse bias, or sorry, in the forward bias, it will act as a very normal diode. You will just replace this diode with a battery, and that's all, which is a V node, as we did in the previous diode models. However, in the reverse bias, it passes the voltage whenever it's less than VZ. For any value of the voltage greater than VZ, then the output will be clipped to VZ. This was one of the applications for Zener. Okay, so let's go to another circuit, another example where we can demonstrate the impact of a Zener, a more interesting example. Okay. Our example is as follows. We have an AC source. We have a resistance. This is typically the same like the first example, but now we have two Zener diodes connected in this manner. It is connected face to face, as you can see here. Let's call this D1 and let's call this D2. And let's see together what will happen in this circuit. So we have an input like this. Let's see what will happen. Let's first start with the positive cycle. In the positive cycle, this is positive and this is negative. So the voltage here is positive. Accordingly, D1 will be forward bias and D2 will be reverse bias. Perfect. Once D1 is a forward bias, then it will have a voltage called V node or V relay. That's true. So in this case, in this positive half cycle, you can replace this by a voltage source like this. And what about the output? And what about, sorry, D2? D2 will pass the input as far as it's lower than VZ. Whenever the output is VZ or greater, then it will pass only VZ. So the maximum voltage here will be VZ. This is the maximum voltage that can pass. So whenever you have this circuit, that means you have here we have V node and here we have VZ. So the output will be V node plus VZ. Let's do it by numbers again. Let's say that this is 10 voltage. And let's say that VZ is 3 voltage. And let's say that V node is 0.5 voltage. Then this 10 will reach here. We replace D1 by a battery, which is 0.5. And the maximum voltage that can pass between these 2 points will be 3 voltage. So the maximum total voltage here is 3.5. However, the input is 10. So you will have something like this. The output will be clipped at 3.5. However, the input is 10. What about the reverse direction? Now you have a negative, positive, negative. So this will be forward and this will be reverse, which is typically the same. So we'll have output like this in the reverse right. So your final output will be something like that. You clip the output to the maximum limit you need. based on your configuration, your Zener diode. So this might be a very interesting circuit whenever you would like to limit your voltage. For example, I have a 20 voltage AC source. However, in my next circuit here, in the next circuit, I need only to pass the voltage whenever it's below 10 times. And if it's higher than 10, I need to clip this voltage. I need to limit this voltage. Then you can directly go to the Zener diode application and you can implement this. If you recognize it well, it is some sort of voltage limiter in order to limit the input voltage to a certain stage. So you can limit the input of the next stage, which is the output of this stage, to any certain value based on your Zener configuration and based on your Zener diode. For example, you can use a VZ equal 3, 5, 7, 9, whatever the voltages, and then you can get different outputs. This is a very interesting application where Zener diodes play an important role. So that's let's now return back to the presentation, and this is the circuit we have. Again, this is some sort of a rectifying circuit, so you can easily monitor it in a very easy manner. That's the end. That's the end of part number part number 4 or part number 2, which is the electrical diode. That's actually typically the first 50% of the course. We have dealt with operational amplifiers and electrical diodes. In the coming 50%, inshallah, we are going to deal with the MOSFETs and the BJT or the bipolar junction transistors. Thank you very much, my dear students, and see you next lecture, week number 7, with MOSFETs.